world today, we make enormous use of plastics, man-made materials. We use them for almost every kind of packaging. And we use them for making different kinds of useful objects. In this film, we'll take a look at one of the most important plastics, polyethylene. This cylinder contains the gas ethene, C2H4. We'll collect some over water in a gas jar. You may have seen the reaction when ethene is shaken up with bromine water, which is coloured. It becomes colourless. This is because the bromine reacts with the ethene by joining onto it, forming dibromoethane, C2H4Br2, which is a colourless compound. Now, many other chemical elements and compounds will join onto ethene, and in fact, ethene will join onto itself. Here's a demonstration in the laboratory. This flask, which has to be completely free of air and water, contains a solvent, and ethene gas is being passed into it. If we add certain substances which act as a catalyst, ethene molecules will come together, joining onto each other to produce a new compound. The catalyst has to be mixed with another substance called a promoter. This is the first constituent. This compound reacts with air and moisture and has to be handled very carefully. This is the second constituent. In it goes. In a very short time, the liquid becomes milky looking and specks of a white solid appear. After a while, there's a lot of the white solid. Switch off the stirrer and it settles to the bottom of the flask. This is polyethylene, a very important plastic. If it's filtered off and dried, it looks like this. It may not look like a plastic, but after melting it, it can be turned into all sorts of articles. What's happened is that the ethene molecules have joined onto each other. Many hundreds of molecules may come together, this process going on and on. If we write the structural formula of ethene, you can see that there are two covalent bonds between the two carbon atoms. This is what happens under the influence of the catalyst. Many ethene molecules come together. The double bonds open up so that a long chain molecule is formed containing many ethene units. The process is called polymerization, and the product is a polymer. It's called poly, meaning many, ethene, polyethene. Now let's look at how polyethene is produced industrially. This is the polyethene plant at BP Chemicals at Grangemouth on the Firth of Forth in Scotland. Many important chemicals are produced here, some starting from crude oil or North Sea gas as a raw material. There's the polyethene section of the plant, those towers on the left. We'll have a look at the plant used to make the polymer, or rather, first of all, at a scale model. The polyethene is produced from ethene in this wide piping. This corresponds to the glass vessel in our laboratory process. Industrially, the glass flask becomes a long metal tube, but in order to have a sufficient volume, this would have to be inconveniently long. It could be made into a circle, but this would still take up room. So it's actually coiled up like this, so that we have a long length of piping in a reasonably small space, in which the polymerization reaction can take place. Here on the model is the bottom of one of the reactor loops. See how it stretches upwards. And here's the top. These containers hold the catalyst. They correspond to the glass tubes we saw in the laboratory apparatus. The catalyst enters the reactor loop, the wide piping, down here. This corresponds to the glass syringe we saw used in the laboratory. This is the model again. And here's the real thing, one of the polyethylene production rigs at Grangemouth. How do they get the ethene they need to make into the polyethylene? They get it by cracking, splitting up ethane. Ethane, C2H6, breaks up on heating to just over 800 degrees C into ethene, C2H4, and hydrogen. The ethane, obtained either from oil or from North Sea gas, is heated by a group of furnaces in the cracking plant. You can see the ends of some of the furnaces. Here's the bottom of a reactor loop again. The ethene is fed in, mixed with a volatile organic carrier. Here's where the catalyst enters. He's going to check the catalyst flow. The whole process goes on continuously, 24 hours a day, 7 days a week. On the model, here are the narrower pipes which carry the product, polyethylene, and carrier up to the top of the plant. There's a tank at the top called the flash tank. As the reaction proceeds, the pressure rises in the reactor loop, and there are 3 valves which work automatically, releasing polyethylene and carrier up one or other of the pipes leading up to the flash tank. The polyethylene and carrier pass up these pipes into the flash tank, the pressure is released, and the solvent boils off with a roaring noise. The solid polyethylene, a white powder, now passes down from the flash tank, and it's dried as it does so. At the foot of the plant, it's carried across into silos. Samples can be taken off. Different polyethylenes can be made for different uses by varying the conditions, and the product must be analysed to make sure it's correct. The gas ethene has polymerized to give this solid polyethylene. In this next part of the process, the white powder is turned into larger pellets of polyethylene. Inside this plant, the powder is first heated so that it melts. Polyethylene is a thermoplastic which can be softened by heating. In this machine, the melted plastic is forced through holes, and it's sliced into little pellets as it emerges by a rapidly revolving metal blade. We'll stop it for a moment so that you can see the blade and the holes through which the plastic comes out. The pellets pass out along a pipe to more storage silos. In the big shed below the silos, there's a packing plant where much of the polyethylene produced by BP Chemicals is put into conveniently sized sacks and containers. BP polyethylene is called Rigidex. Filling these plastic sacks and packing them is a fascinating automated process. Here, the sacks are counted, so that after a certain number has passed through, the next batch can be turned through 90 degrees for stacking on a pallet. Again, this is a continuous process. It gives you some idea of how much polyethylene is used nowadays. All this will soon go out to customers. Larger quantities of the pellets can be run directly into road tanker vehicles for transport to the customers. What happens to this raw polyethylene when it gets to the customer's factory? This is the BXL plastics plant on the Wirral in Cheshire. Here, polyethylene sheet is produced for making into plastic bags and sacks and other products. The tanker is unloaded through a pipeline into silos again. Different silos may contain different grades of polyethylene, which can be blended as necessary. Inside the plant, the granules are mixed in the correct proportions, and any colouring matter needed can also be added. The process is guided using computers from this control room. The right blend of polyethylenes is delivered to the bottom of the plant, where it's melted in the absence of air. The melted plastic is then forced up through a circular slot. Air is blown in the middle and on the outside, and this cools the polyethylene as it emerges, and a sort of huge bubble is produced. You can see the slots through which the air is blown in. Although it may look stationary, the bubble is continuously on the move upwards. At the top, it's squashed flat. This produces a double thickness of plastic sheet which passes over and downwards again. As it passes downwards, instruments check it to make sure it's the right thickness. At the bottom, blades slice the flattened sausage so that 2 layers of sheet are produced. Here's one blade, and there's another at the other side. 2 big rolls of plastic sheet are produced, one at each side of the machine. This roll weighs about 1.5 tons and has about 15,000 meters of polyethylene sheet on it. A black pigment was added here. This is for making silage bags. Other colours can be produced. The rolls pass into another area where they can be cut to different widths if necessary. Once again, this gives some idea of how much polyethylene, this time as sheet, is used today. The polyethylene pellets can be treated in another way, for making bottles, for example. This machine in the development laboratory back at Grangemouth melts the plastic, then blows it into bottle-shaped moulds. Many different kinds of article can be made out of polyethylene using all kinds of different processes. It's very useful for electrical insulation. The fuel filler pipe for a motor car. Piping of all kinds for many different purposes. You can see some actually in use here in one of the BP Chemicals development laboratories. It's lightweight, strong, and doesn't corrode easily. An electron microscopist at Grangemouth examines a polyethylene sample in the electron microscope. Those worm-like shapes are polyethylene crystals. Each contains long folded carbon chains of the polymer. A test being carried out which shows how polyethylene sheet, for example, has different properties in different directions because of the way in which the carbon chains are pulled into certain patterns when the sheet is produced. If a disc of the sheet is heated, it shrinks more in one direction than the other. This means that it behaves differently when it's pulled, say, in two different directions at right angles. Here, in one direction, it forms a narrow neck which stretches and stretches and stretches as the tension is increased. Tests of this kind are very important to people making things out of the plastic. It's still stretching. Remember, this has to do with the way in which the carbon chains are arranged in the sheet. In a direction at right angles to that in the first test, a specimen from the same polyethylene sheet behaves quite differently. Testing plastic products is very important. Here, a big polyethylene barrel is filled with water under pressure to see if it leaks. Compare it with the empty one. It's being inflated by the water. When the bottom becomes rounded, it falls over, but it doesn't spring any leaks. This polyethylene barrel, filled with antifreeze solution, has been stored at -18 degrees C. Has it become brittle? Here's one kind of test. It's dropped onto a rigid surface. The test was carried out a number of times with the barrel falling at different angles. It distorted, but it didn't burst. It's very important to know just how safe is any application of polyethylene, or of any material for that matter. This polyethylene pipe sample has been pressure tested to failure, and this shows typical plastic yield behavior. As plastics are developed, it's necessary to investigate them as they do in these laboratories at BP Chemicals in Grangemouth. We've looked at the manufacture and some uses of just one plastic, but a very important one, which plays a large part in the world as we know it today.